An important question we should address is, how do we then get magnitudes from that reduced data? And for that, we need to photometrically calibrate the data. The way we do it is essentially by performing aperture photometry. We will be measuring the counts, essentially the number of electrons that were collected for a region that corresponds to a specific star. And the way we calibrate the data is by observing a star for which we already know the magnitude very well, so that we obtain what we call the 0 point of the image. What we can do is we can look at the difference between the magnitude of the new star that we're trying to find the magnitude for and the magnitude of the reference star for which we know the magnitude. And we can actually look at minus 2.5 log 10 of the ratio of the counts. Remember just the definition of magnitudes. And typically we can apply this equation directly if the counts have been obtained with the same exposure time. If not, we need to normalize by the exposure time. Otherwise, we'll just get more counts because we exposed for longer. In general, what we want to be able to do is to put an aperture and estimate the magnitude, in this case for the R-band filter for any star, essentially by writing an equation that is 2.5 log 10 of the counts of that specific star in the R-band plus some 0 point, some photometric 0 point. In this case, if we're using a reference star, the 0 point is simply obtained by using the magnitude we know from the reference star plus 2.5 log 10 of the number of counts that we obtained for that reference star. And the other important thing to point out is that if we're doing the same exposure times, all these equations will work straight away. If not, we need to normalize by the exposure time. If your reference star was observed for a much shorter amount of time or much longer amount of time than your real data. So this is what we can see here as well, that if we observe a reference star for which we know the reference magnitude, we can then reduce the data in the same way for the reference star and also put an aperture around it in the same way. And what we're doing is we're doing the sum of all counts within the aperture. Because of the definition of magnitudes, then we can write this equation right here. Again, noting that if the exposure time is not the same, you need to normalize by dividing the counts by the corresponding exposure time first. Once that is done, we can also write something like this. And finally, we will be able to get an equation that will be valid for any star or object that will be minus 2.5 log 10 of the counts of that object plus some 0 point. The 0 point will be able to be obtained essentially if you know the magnitude of a specific star and you actually look at the counts by using the same system as for your general object. In your lecture notes, you also have specific examples, such as this one, of how to get magnitudes from reduced data. For this specific example, say that the magnitude of your reference star is 10, and that when you observe that star and you do the same data reduction process as for your real image that is shown on this side, in 100 seconds, you get a huge number of counts. This is a million counts. If you do that, you can determine the 0 point in counts here. It's the magnitude of your reference star, that's 10.0, plus 2.5 log 10 of 1 million counts. And this implies that the 0 point for 100 seconds will be 25.0. What this implies is that we can then write this very simple equation that will be valid for anything, provided you're doing an exposure of 100 seconds. With exposures of 100 seconds, and in the R-band and with the same instrument, if you plug in the counts, and then you add 25, you'll be able to get the magnitudes of your sources. For example, assuming that this object, once you put an aperture and you sum all the counts, yields 7,000, what magnitude in the R-band will that star have? This is very simple. We've already calculated the 0 point to be 25. We only need to plug in 7,000 into the equation, and we'll see that this specific star would have an R-band magnitude of 15.4. With this equation for this specific data set, this is how we would be able to measure the magnitudes of all these different stars. And if we want to have, for example, a B minus R color, what we need to do is the same process, but with the B band filter. But the same thing will apply. And finally, we'll be able to get a color by looking at the difference of magnitudes, which would allow us to, for example, estimate the temperature of that star and many other properties, as we shall see in section 8.